Our final speaker today, at the end. So Adam Sherer of Cadence Design Systems is a system verification account technical executive, and he's going to be talking about meeting functional safety requirements for automotive applications. Adam is a system verification account technical executive at Cadence. His 27 years of experience in verification and software engineering also includes roles in product management, applications engineering, accelerator standards development, and R&D. Adam received his MS in EE from the University of Rochester with research published in the IEEE transactions on CAD. His BSEE and BACS were received from SUNY in Buffalo, and he also holds a 2017 patent in verification technology. He's speaking from Boston. It's fairly early there, so good morning, Adam. Thank you.
Thank you, and good afternoon. So I'm going to hop right in, keep us on time with some good information. As you can see, the slide title is Ann Keffer. So this is her material I'm presenting on her behalf today. So I'm going to get right to it here today. So you've seen presentations through the day today. I'll spend just a little bit of time on these introductory slides, as I think some of the themes may be things you've seen already today. All right, so we're seeing certainly a high level of interest. I think the point I would add here is we often see the idea of this mind-off autonomous vehicle, and when we see companies advertising this, when we've gone to some of the automotive conferences, this is still some time away, and there's a lot of engineering that we're all going to do up through these steps to get to full automation. The systems can be created, but they need to be functionally correct, they need to be high reliability, and they need to be secure and safe into the future. And that's what's going to occupy our engineering and really provide, I think, a lot of engineering activity and interest over the next several years. And let me move ahead. There we are. As I think you've seen, the foundation standard for automotive safety is IEC 61508, and it has generated a number of standards around it that are all derived. And the 26262 defines the processes we need to follow for safety verification, and for it alludes to the system and functional verification as well. The overall system performance necessary, the documentation needed, and the tools compliance process. Today we're going to focus primarily on the safety verification aspects. So ASIL determination. So this is the critical aspect that we all need to address. We identify a potential failure or malfunction here, ABS system failure. It's a very high level statement. And there's a goal, which again is a high level statement here, preventing ABS failure. So we need to analyze the hazard itself, what could happen, how can that hazard be triggered, and then what's the risk associated with that hazard. How harmful will it be, how controllable is it in the system, and based on those parameters, we're going to determine the ASIL level that we need to achieve to mitigate that risk. Now, what we will address, and I think you've heard from some of the other presenters today, is while a lot of the safety analysis that's been developed in the processes, right, the process we're talking about here is 40, 50 years old and longer, right? The whole failure mechanism, identifying the effects, the diagnostics, this is a long-held process. The tube suit, as OneSpin has been represented before me, they've been in business, I believe, for about 100 years, looking at safety systems. So it's not a new concept. What we're all addressing, though, is the level of precise information that we need to generate in the semiconductor space, because the number of points of failure in these types of systems is much, much higher than we've seen in the mechanical systems that led to a lot of these standards. So the safety principles, there's systemic failures, like a software bug. This should be addressed by processes of planning, the documentation, the specification. We need to make sure that systemic failures are essentially designed out and hopefully verified out of the system. Given stability in the systemic environment, there is always the possibility of random failures. Component malfunction, noise injection, aging, right? These are all different aspects. They may be permanent, they may be transient effects, and we need to define safety mechanisms in order to catch and to observe these failures and then provide an appropriate system response. The ability of the safety mechanisms to identify those failures is calculated into the reliability and verification rates, and we need to identify a diagnostic coverage requirement based on the ASIL that we define, right? So the ASIL is defined primarily on the potential failure, the diagnostic coverage, the failure rates associated. We need to make sure that the system can kind of live up to that ASIL level. And that's really the challenge. And that's why you see that circulation here between the design analysis and verification, is that these elements are kind of co-developed, and we need to make sure that the system is whole between those two. So what is the functional safety analysis? The definition of failure modes as we described, the determination of safety mechanisms, right? So we have to have a balance, right? And the balance here is that there needs to be sufficient safety mechanisms to achieve the ASIL level that we've defined, but we also need to maintain system performance, area, power, right? The normal constraints of the design itself. And that's the balance that we need to achieve between the kind of systemic verification and the safety verification in our system. So defining functional safety, the typical approach, again, and this is the practice that's been conducted for decades in safety-related systems, is very structured. And it needs to be structured in part to make sure that we've obviously built this correctly, but it needs to be structured for audit and for failure checking should something go wrong in the system as well. Right? It's part of the documentation approach, is that it is structured throughout the process. So define the failure modes, the mechanisms, the diagnostic coverage, feeding into the safety analysis, like a failure mode effect diagnostic analysis, and then generating the hardware metrics to demonstrate that we've achieved the goals of the FMEDA. Right? And you can see the ASIL levels and the appropriate failure rates. Right? This is straight from the ISO standard. So the importance of failure modes and failure mode effects and diagnostic analysis. It's a requirement in 26262. It's a requirement in the other related standards as well. Again, it's not a practice localized to 26262, but it's needed to verify the number of safety mechanisms, right, because they're connected to the failure modes themselves, and whatever diagnostic coverage properties are claimed, right? So without automation, right, one way to address this is to have a safety expert analyzing the system using a statistical analysis, using historic trends, and identify a claim diagnostic. That isn't sufficient, certainly in the level of complexity associated with a semiconductor. And our observation over the past several years, we've been building technology in this space since 2013, is the requirements coming from the OEMs to the tier ones, to the semiconductor, to the IP providers, even to us as EDA, are increasing. There's an increasing need for detailed, calculated analysis. And I think you've seen some of that from my colleagues in the previous presentations. So what do we need to do? Well, we need to capture and analyze the goals. And this is a subset of a typical FMEDA analysis where we're looking at a particular failure mode. So we need to capture, in fact, you can see this in a spreadsheet form. This is a common approach. Again, as we've gone to industry events, we see this type of approach. I think it was either a Daimler speaker or a GM speaker a few years ago in a conference in Berlin that identified 20,000 pages of this for a vehicle, right? So this can be enormously extensive for a full modern vehicle. So we identify there's an ID, again, this is for traceability, a particular part, again, so that we can localize it to a specific element of the overall automotive system, subparts, again, helping us in the traceability, down to a particular failure mode. Then we're going to look at the number of gates and the flops. These things are going to help us identify the potential failure rates in that subset of the system. So we identify a failure rate, the safe fraction of faults in this space, the failure mode distribution, diagnostic coverage achieved, and a known hardware safety mechanism. All right, and our goal is to continue to do the simulation, the formal analysis, the hardware emulation, all of the analysis techniques that we can apply to improve these numbers to achieve the proper diagnostic coverage that we're looking for and the overall ASIL level. So what we've observed, and hopefully you can hear this in the presentation, is that the systemic failure analysis, the functional verification, and the random failure, the safety verification, these are kind of mirrors of the same flows. And they really need to be in order for us to build workflows for this in our semiconductor teams, to leverage technologies that are known well working in these flows. All right, so simply stated, on the functional verification side, should be quite familiar to you. Set of functional requirements, some type of functional management control that looks at verification plans, identifies tests, and submits that into a verification environment upon which we're going to run verification technologies such as formal analysis, simulation, hardware verification. This can be extended for analog as well. Gather coverage, track it back to the verification reporting. On the safety verification side, you can see a mirror of this. All right, so the FMEDA is similar to that verification planning. We need to be able to run the diagnostic coverage, so that's the functional management, creating fault lists, optimizing or reducing the fault lists, and then running the campaigns with verification technologies that gather effectively the equivalent of functional coverage in terms of a comprehensive faults results database. All right, and like that flow that we showed earlier between the design and the verification sides, these flows are circular, right? And we will need to anneal the verification over time. And what do we mean? Well, on the functional verification side, we continue to add more and more testing to achieve our functional coverage goals. On the safety, we're going to add new safety mechanisms, make sure that we've covered all of the failure modes we need, and generate better and better diagnostic coverage to achieve the measurements that we're looking for. So in detail, there is a stepwise flow. We do capture and analyze the failure mode effects and diagnostic analysis, prepare the fault campaign, run and rank the tests. Again, this is for optimizing our a verification flow for safety, compile and elaborate, generate a fault database, reduce that fault through fault equivalence, undetectable faults, things like that. Run the safety verification. Here, when we say good simulation, good machine simulation, with the capture and the save checkpointing, these are all optimizations to generate fast simulation, whether it's a serial fault simulation or a concurrent fault simulation, and generate data, right? And there's a debug process associated with this as well for potentially detected faults, and that may include formal analysis to help us debug those potentially detected faults, or additional test generation. There are a number of ways we can go about that. And then we generate a report, map it back to the FMEDA, and determine if we've done enough. All right, so this could be an iterative process. And not surprisingly, my short advertisement here today, this is what where our focus is. It's on technologies to fill each of the steps in this overall flow. So flow support, we start with an architectural FMEDA flow. That's a rough estimation of the overall metrics. We're going to do some analysis at that level, and that's sort of a projection. And we need to do that to determine if we have sufficient safety mechanisms defined for the FMEDA that we've developed. Right? So that initial analysis we've done could lead to additional design work to add more safety mechanisms, something like that. Then we're going to get into the detailed FMEDA flow, the thing you saw on the previous slide. That's going to do a fine-grained analysis, that is simulation per failure mode, to determine the effect of that safety mechanism and to develop the diagnostic coverage. That's going to lead to evidence, all right, and this is the simulation, formal emulation evidence necessary to demonstrate that we've achieved the safety goals. All of that is traceable and recorded in these overall systems. Certainly, this is the tool chain that Cadence is developing and deploying with our customers today. And so, in summary, the flow needs to be integrated between functional and safety with the flows and engines. This is absolutely necessary. The safety solution needs to be incremental or added to the functional verification that you all do today. That's absolutely critical to making this part of the process and developing a safety culture inside your companies. We need a verification plan on the functional side with a similar FMEDA plan, and it all needs to be based on metrics and analysis so that it's traceable, recordable, and we develop the data proof that you need to go through compliance. We need to automate that flow to reduce the human effort wherever possible. That's actually the main part of our engineering today. There's got to be an execution core. In the end, we do need to do some pretty heavyweight simulations and formal analysis. So these engines need to be optimized for turnaround time, that's the TAT, and optimized for general run speed. And that's absolutely what we're working on today. And we also just need to assure that we're not running wasted cycles. So fault reduction using formal engines, things like that, absolutely part of the flow. And that's what we're developing as a comprehensive solution for functional safety. So I know this is quite quick, trying to stay within our time period here. This was part of a longer tutorial that we did together with ARM. I think Andrew Betts is somewhere in the ether here today, or possibly in the room. So Andrew is from ARM. He and I co-presented at DVCon Europe a few weeks back. And so that longer tutorial is going to be available from the DVCon Europe as well. So you can see this slide with TVS, the longer tutorial at DVClub, I'm sorry, at DVCon Europe. And by all means, you can contact Andrew or myself for additional follow-up. So I think that leaves me with 15 seconds available for questions, Sarah and Mike.
I guess that's just long enough to say thank you. I would add as well, I was at DVCon Europe, and I did see the presentation from Andrew Betts and from Adam, and I would recommend it. It's a very good presentation. So I'll use your 15 seconds as a plug for your presentation, Adam. That's probably the best use of that 15 seconds.
Brilliant.
Thanks, Adam. Thank you very much.